I just posted a link for sharing to read. Let me know if you can use that and if it works. It's in the Discord, in the stream documents. I've never done this before, so I don't know how it works. I imagine I can probably... I think it works. I don't know what that means. I'm sorry. I don't know. French? I think that's French. I have no idea. Let me also try to see if I type something, if it'll update automatically or if you'll have to refresh it manually. Doesn't seem to be showing up, but you can, I assume, refresh. Yeah, you can refresh the page and it'll show up. So it seems like, yeah, it works. Okay, well that's cool. So now you have that. Okay, so I haven't done anything on this project since we left off a couple hours ago. But we know what we're going to do now. So last we left off, we reviewed all of these theorems and results and some of the changes I had made. And we also wrote down in our appendix, we wrote these proofs for uniform convergence and Cauchy sequences. So we don't need to use a metric function. That we can actually just use our script A function, which is great. Okay, so that's nice. So now we're going to start on the next section, which is actually going to go above power series. We're going to do a new section. I don't know if there's any word that... Yeah, that's fine. I'm just gonna leave it how that is. So we're gonna do derivatives, which is exciting. The plan is we're going to state our definition for a derivative. We're going to prove sort of the standard derivative properties, and we're also going to find some different, maybe some different properties for you know, that apply specifically to our space that we can use. We'll just start off sort of with the standard, some, you know, prologue. So So derivatives are just like standard, a limit of difference quotient, but the only difference is the idea of a quotient is controlled by cancellation. So when we define a function, so we'll have our functions. So we'll say let D be a subset of A, then and some function f map D to our space. Let's say have no isolated points, and let f map D to A. We'll say be any function, be continuous actually. Then for each point x and d, we define the derivative f prime at x, or df of x, so d for derivative, as follows. So we have limit as we'll say how do I want to do this? So there's several ways of defining a derivative, actually. Especially in this space, there's quite a lot of control. So in my paper, I actually define it in my earlier drafts. I have a very specific definition. I define it in this particular way. So this is actually both variables, A and B, are both limiting to, whatever the point is, x. And so that's sort of the standard way that I've done these derivatives. There's a lot of proofs finding out how these are the same as this sort of usual the usual way of taking a derivative, where you have only one variable that's moving around. But they're not always the same, and there's some interesting cases where they are not the same. I think, though, the theorems and proofs end up being rather easy with this sort of derivative definition. We might be okay not using it. Welcome. Yeah, so we're gonna have to find out. I guess how we want to structure this. So most of these theorems will be fine, regardless if we use the usual method of derivative or this other fancy way of differentiating. Let's see. I think many of these will not be required. So we have one theorem where if we have it differentiable in this stronger sense, then its derivative is a continuous function. I think it's required. In fact, I think it's maybe, depending on the domain, it's actually equivalent to it being continuous. So we'll have to figure out if we want to do it with this way or the standard way. Okay, I think it's actually just this one function, actually. I think it's, or this theorem. I think this is the only theorem where it happens. There might be other cases for derivatives and antiderivatives. But let's start out with the weaker derivative, and we'll see what we can do when we run into problems, if we run into problems. I think we might be okay, though. But let's just sort of go ahead with this. So we'll go ahead with the standard definition, which is nice. So we'll start out with this standard definition. So I'll do, oh gosh, what variable should we use? Let's do limit as, we'll do y goes to x of standard fractions. We have f of y minus f of x over y minus x. So this is sort of a standard one variable limit, and we'll have the f of x is defined as equaling this thing. Also, we don't want to have our domain be D. That would be confusing, so I'll use S. So this is our formal definition that we're going to be starting with. So, so our derivative is defined using this sort of the standard method, but we can use any set, any subset of our more general space A, so long as it doesn't have any isolated points, because that'll sort of, you know, mess it up. And we'll let, if f is a continuous function, so it has to be continuous for this derivative to be defined. Then for each point x in this space S, we define the derivative as this limit, where the variable of this limit, y, is staying inside the domain set S, using the subspace topology. So essentially what that means equivalently is we're saying for every sequence of y, which is approaching x, eventually, if we restrict y to be inside the set S and approaching x, then we want we want this quotient to eventually be defined, and we also want that to have a limit. So if you recall, division, even if we restrict our variable y to not equal x, so even if the denominator is non-zero, division is not always defined. So actually what we want to say is that we just want this fraction to eventually be defined. Because we're not operating in a field here, so so I'll just make this note. So given that division is not always defined, we just require that as y approaches x in S, eventually the fraction is defined. So eventually the fraction will be defined, and once we get to that space, that region where it is defined, then we want also to have this convergent limit. So this will have a lot of the usual, so the normal derivative properties are pretty straightforward. So most of the standard laws for derivatives have the same proofs. So actually, something to notice here is that the way that I'm actually defining this, the specific way I'm defining this, actually we haven't we haven't really made very many assumptions on the space S. We haven't assumed that it's open. We've just assumed that it has no isolated points. So for example, if we had S just be the complex plane, and for example, if F always happened to output a complex number, this would just be the complex derivative. Or if we had S being a subset of the real line, and if F always outputted some real number, then this would just be the real derivative. So the proofs here, in addition to the fact that many of these proofs are going to be extremely similar, they're actually the same proofs in that they prove the same properties for the weaker sorts of derivatives. So we'll just get restarted here. So so we want several theorems for all these laws. So we want a theorem for addition, we want a theorem for the product rule, we want a theorem for some other simple functions, like we want derivatives of the constants and derivatives of polynomials. So constants, the identity function. We'll also want the chain rule. So each of these will have their own theorems, and they will require proofs. So I'll just sort of set all these up real quick. So we can probably leave the constants and identity function. Those are super simple. Those are super simple derivatives that we can prove. They're very straightforward, and actually they come out pretty much immediately from the difference quotient formula. So we can have let F map A to so it's going to maps to any x to some constant. So let C and A, B, and F have this map, then df of x equals 0 for all x. So this one is going to be super simple. So this is derivative of a constant is 0, and the proof is literally just one line, which is just we have df of x is the limit as y goes to x of this fraction c minus c over y minus x, which is 0. So that's trivial. Literally just if f is constant, then the numerator is just always 0. And actually we can make this visually much shorter even than it is by putting it out like that. Yeah, super simple. So that's just a one-line proof. The identity function is not too much different. Let me actually be a little more specific here. X in A has derivative of f of x is 1 for all x in A. And the proof of this is also one line, which is df of x. This is just the limit. We have y going to x, and we have our fraction. We have y minus x over y minus x, which is just 1 again. So once again, this is just a one-line proof. If f is the identity function, then the numerator is the same as the denominator. So it just trivially simplifies down to 1. Next we can do the addition law. So we can say let f and g map s 2a be differentiable, then df plus dg is df plus g. So the derivative of f plus the derivative of g is the derivative of the sum. And the way that we can do that is we have, we're just going to use the definition, so df of x plus dg of x, this will be, so we'll have two different limits. We'll have y going to x, and we'll have in the numerator, for the derivative of f, it's f of y minus f of x over y minus x. And we also have plus the same exact limit of this, but for g. And this is when we merge the fractions, that's just the sum. So we can merge the fractions, and also when we merge them, let me put these together. Yeah, so when we sum them up, we just have these two different limits, and that's when we merge the fractions, they're just like that, and we can actually just rearrange the terms as, so we can move this minus g of x, or sorry, this positive g of y, we can shuffle that over here, and then we can put these in parentheses. This is f of y plus g of y, and then minus, and we can factor out this minus sign, f of x plus g of x, but then that's just the derivative of f plus g at the point x. So this is pretty standard as well. Let me just reformat, so make this a little prettier. Oops. I can put this on here, and this one down. We can also actually do this in reverse order. I think if it might flow a little better. So I'll start with df plus g, and then we'll expand this out to its definition. That gives us this next term. Let's see, where were we? That was this one. And then we have this one, and that's this. Okay. Well, let's get all these aligned. Oh, I didn't do a new line there. Okay, that's not so bad. And we can put this one on another line as well if we want. Space is not quite at a premium, I think. Okay, so that's the sum law. And this is super easy as well. So because both of these derivatives are defined, then eventually both of these difference quotients are defined, and their limits exist. And then we can just merge them together, just using the laws of fractions. And in case it's not clear, laws of fractions do work like this. So if we have something that can be divided by something else, and we add something else that can be divided by something else, we can merge the fractions in this context. You can probably prove that one from the definitions of proportionality, that if you have two different fractions that exist, then you also get these. So the fact that we maybe can't always divide things is okay, because we've assumed by premise that both of these are differentiable, that the derivative limits do exist. So that's it for this proof. So we can close this off. And And now that's the sum rule. Next we have the product rule. So in order to do the product rule, that one's also going to be pretty similar. So we're just going to start off by doing the definition. So the definition is that d of fg at x, so this is just a limit. We have y going to x of this fraction. So this fraction is, actually I think this one is maybe, or maybe I'm thinking of the chain rule. One of these is slightly more complicated than the other. No, this one's okay. Yeah, okay. The chain rule has, the formal proof for the chain rule, you have to do something a little extra, but we'll get there. So this fraction, so we have f of x times g of x, actually, sorry, this is y. F of x times, f of y times g of y minus f of x times g of x divided by y minus x. And so we can reformat that. So what we want to have is something similar to the sum rule. Instead of summation, so d of f times g, this will be, we have left d right plus right d left. And I think if I just write them like this, that's clear enough, hopefully. Okay. All right, so down, so we're right here. Okay, so so this is our definition for our product, our derivative of our product. Now we want to try to turn this into a format that sort of fits this. So first what we'll do is we'll try to sort of tease out this first term, f times g d of g. And so in order to do that, we'll want something like, say we add and subtract, you know, f of y, g of x, or something. Or something like that. Actually, there's a specific way to do it. Oh yeah, okay. Yeah, so we want to end up with FDG, so from here, because there is a specific way, we have, oh yeah, so, okay, interesting. So we'll do, gosh, call it G, f of y minus f of x, and this gives us, when we distribute this out, this would give us a minus f of x g of y, so we have to add that back in to get it out. And because we have added this back in, we can now factor as here, we have common factor of f of x, so we can factor that out, and we get just like that. Yes. So essentially, in order to get this, we just add and subtract f of x times g of y. And then what we can do from here is we can separate these out into separate limits. So we have two different sort of summations here. But we know if we separate these, so we just have these two different things. And we're sort of skipping steps a little bit here, because we haven't fully asserted that we can do these fractions. That's going to work out in the end. But let's just work on we just sort of want to get the end result. Oh, where did I? Oh, that's why. Okay, let's put that there. Okay, so we split up the fraction, and we can actually go a step further. We can pull out a g of y here to the front. And over on the other term, we can pull out an f of x. And pulling out the f of x is actually easier because there's no y there. So yeah, so we end up with something like this. We could also not quite do the double limit just yet, if you don't want to. Yeah. Anyway, so when we work this out, what we want to say is that because, especially in this first limit, because both of these g of y is convergent to g of x, then this should be, we should just be able to factor this out from our various, so this will be dfx, and this will end up as f of x times dgx. And if we're concerned, so we can always do this in reverse order, and actually maybe that's, whoops, I forgot a line environment does not like white space. So if we're concerned, we can do this in reverse order. So we can say, you know, let's start out with this term, and we say, well, this is just equal to, you know, this limit here, just like this. And then we can follow that with this line and then this line. Why is it doing that? This is why. I think that should fix it. Okay, yes. Yeah, so we have g times the derivative of f. That'll give us this g. And if we're ultra concerned, we can also put this g of x out here. Yeah, and that says we have g of x times this limit of y, f of x times this limit of g, and we can add an extra line here, so we can, maybe that's okay. I think it's okay. It's probably okay. Okay, sure. So we get these, we merge the fractions together, we simplify, and then we just get this derivative. So that's the product rule. The chain rule is the one that's a little finicky. So I'll add exposition later, I think. The chain rule is the one that's a little finicky. So sort of the proof sketch is we want to say, you know, when we do our derivative, so d of f of g of x, we want to say this is the limit as y goes to x of this fraction. So we have f of g of y minus f of g of x, and we divide this by y minus x. So this is the normal, so this is the derivative definition. I mean, what we want to be able to say is that this is the same as if we do, so we have this whole thing, it's supposed to be f prime of, yeah, g of x. So we want to do in the bottom, instead of having y minus x, we want to do g of y minus g of x. But then we'll multiply by g of y minus g of x and divide by y minus x. So this is sort of what we want to do. If this whole fail, yeah. So this is sort of what we want to do. but we don't actually know if this is valid or not. So we're not actually sure if this is going to be, I mean, we are sure that this is going to be okay. But the problem is that we don't know if g of y minus g of x is 0 or not. So in this sketch, we'll say, take the case where g of y minus g of x is non-zero. So where eventually, as y goes to x, so we'll take this case, then we are able to do this. So this right side, this just ends up being, of course we just have, assuming these two things are convergent, then this will just end up being the first limit. So the limit as we'll have, instead of y, we'll have z going to g of x, and we'll have this fraction f of z minus f of g of x divided by z minus g of x, and then we'll multiply this by this limit y goes to x of the fraction g of y minus g of x over y minus x. Let me also double check these. Yeah, let me do these in reverse order also, just like how I did the product ones. I'll rearrange these. That way, we'll have this term equaling these limits and that'll be equal to this line, which is then equal to this line, which is equal to that. Yes, okay. So back down here. So if we assume we eventually have this limit, then we can say write down, oh gosh, I got away from myself. This one. So you can say this will end up being this limit, and then eventually this will also be, let me put some alignments here. Yeah, so we'll have, eventually this will be this, these product of limits, and both of these limits will reduce down. So the first one is just the derivative of f at g of x. Well, I guess really I just want to do f prime, because I don't want to get too caught up in the notation. So this will be f prime of g of x, and then this second limit will be times g prime at x. So this is if the terms are never 0. We can also do this in reverse order. So we'll start out with this one. This is just these product of limits. Because both of these converge, we also know that this is a limit of the product, which is then equal to that, which is equal to this. Yeah, so actually we can do an intermediary sort of step here if we would like to just be super clear that this term right here is actually, we can just do this change of variables. So we can do y goes to x of g of y, and then g of x. The reason that we can do that, this change of variables, so we're going from here, this g to this y, we know that g of x is continuous. So if y is going to x, then g of y is going to g of x. So we're just doing this change of variables where y is z. So sort of intuitively, as if we do this change, we know this limit converges. So for any way that z is approaching g of x, this fraction will converge. So in particular, if we approach it on some direction that is enabled by g, then this will still converge. Okay, so all of these limits check out. So we can do this change of variables. We can merge these together, and this just becomes this one fraction, which is this. So instead, so this is the case where eventually this is never 0. So then we have all of this. Instead, alternatively, so instead we can define a function I think we want to do q of y is how we do it. Yeah, something like that. So do q of y so we'll do a piecewise function and the definition for this is so we'll have q of y equal to a case function. In the first case, we want it to just be equal to sort of this difference quotient. So how can we do that? So what we want is for q of y to always be equal to this difference quotient. No, this one. Yes, this one. So we want it to be equal to this difference quotient. So we'll have this difference quotient in the case that g of y is non-zero. Otherwise, we want it to be equal to actually just the limit that we want it to end up as. Which is d of f of g of x. In the case that g of x is 0, or sorry, g of y is g of x. I think. Yeah. So if we do it this way, let me get some spacing here. Yeah, so if we do it this way, essentially what we want is, what we're going to show is that eventually q of y, this function, is always equal to this difference quotient. So the way to prove that is, so we have, so we can solve this limit first. So that the limit of as y goes to x of q of y is just equal to dfg of x. or we can, yeah. And the reason that this is the case is we can essentially just separate this up into subsequences. So if we take, or rather actually, let me do it a slightly different way. So if we have the case where eventually g of y minus g of x is non-zero, then we this whole proof checks out. If the above case fails, then we have some approach for which y goes to x while g of y minus g of x equals 0. So it follows that g prime at x is 0. This just follows from sort of the definition yeah, so this just sort of follows from the definition as a difference quotient. Is there any reason I don't use limits? The right arrow notation is just compact. It's just quick in the text. Limits also don't sort of fit into text super well. Also, since y is the variable of the limit, it would sort of be redundant, I guess. That's sort of the only reason. Yeah. Yeah. Mostly it's just kind of lazy, and I think it kind of looks nice, I guess. But yeah, so if we have, if this fails, then we don't eventually have yeah, maybe a little bit. But yeah, so if this fails, then we don't eventually always have g of y minus g of x non-zero. But if this fails, then we have to have some path to approach y going to x, which always has this equaling 0. So it follows that since this is just the numerator of the difference quotient, then g prime of x is just 0. In this case, we have so we'll have right, yeah, okay. Let me do a thing. Yeah, so if this fails, we have, so eventually g prime of x is 0. We can define blah blah blah. So we have so a piecewise function q of y defined using this. So what actually do I want? I think I want because I'm trying to show that these are equal. This would be the derivative for d of f of g, and this other one is going to be the derivative for also, there's your cursor. I think this is not going to work in the long term, actually. If more than like 10 people are clicking on the thing, it's going to get very fun. Yeah, so okay. If this fails, we'll have, I'm really brain farting right now. So the purpose is to define this function. Okay, I see. Okay. Yeah. So instead we have g prime is 0. In this case, we define this function defined like this, and actually the second one we want g prime of x times f prime of g of x. That's what we want, yes. So if we have g of y equaling g of x, then f of g of y equals f of g of x. So in either case, q of y equals 0 is identical to the difference quotient. Actually, we want to do so we want to do this full sort of split out thing, this whole thingy. So otherwise we have this. So if we have blah blah blah, actually what we can do is we can do, oh, I don't know. Yeah, I think we want to take this whole thing and sort of split it up like this. I also don't want to have a limit there inside the piecewise function. That's the thing we're taking the limit of. Yes. So if we have g of why your cursor, I don't know. Maybe you have to click somewhere else. I could also try moving it. No, I can't. That's funny. Because it's stuck there forever. Okay, so if we have, so we have, in this case, if oh, it's gone now. So if we have g of y equals g of x, then this is, this minus that is 0. So both cases, yeah, so both, so the difference quotient is 0 in either case. And q of y is just this fraction f of g of y minus f of g of x over y minus x. Yeah, I think. G prime is 0. So by splitting each of the cases individually limit to our g prime of x, f prime of g of x, proving the limit. Okay, yes. So we first solve this simple case, which is we assume that this is always non-zero. Then we can split up these limits like so. If this fails, then we have to have this difference 0. So then this difference quotient g prime is 0. In this case, we can define this piecewise function q like this. If we have our gy equals g of x, in this case, then this difference is going to be 0. So the difference quotient is 0, and in either case, q of y is just this fraction. Each of these cases individually limit, so both of these are solved. So this one is trivial because there's no, y is just not there. And this one has already been solved up here. So each of these cases individually limit to our g prime of x times f prime of g of x, and that proves the limit. And the limit is, I haven't actually put it in the thing, so that'll be the derivative, so if f g mapping some domain S to A are differentiable, then the derivative of f of g of x, and maybe want to do well, that's probably fine. This is g prime of x times f prime of g of x. We can also do like that. Very fancy. This one's missing a parenthesis for some reason. No, that's right. Okay. So this looks good. I can change this a little bit. Okay, so it looks like we're good so far. So I can probably add a little more exposition in between. So blah blah. No isolate points. This is continuous. Each point x, we define this derivative as follows. Okay, so the limit takes y and s using the subspace topology. We could say here's this and this. So over here we can add some text. So what would we want to describe this as? This proof. I guess we don't really need to be super descriptive. this proof, so yeah, I guess we don't really need any description. Yeah, maybe we'll add some more description here later. I think this is fine as is. Okay, so that's the chain rule. We have the chain rule, we have the sum rule, the product rule, constants. We have, oh yeah, I can change these a little bit. Okay, so that's good. So we have all sort of these standard derivatives. The next one that we want to do, so we can do some more complicated ones. So we can do, we can do the reciprocal. So the function f such that x maps to x inverse has df equal, actually you can say f prime of x equaling negative x to the minus 2 for all x in a star. That's our set of units. So if we have something, if we have a function, our inverse function, which outputs units, then we get this standard expected derivative. And the proof for that is also the same. So we just have limit as y goes to x of, we have y inverse minus x inverse, whoopsies, there we go, divided by y minus x. Well, we can just let's see, I think we can, how do they do this over here? Because I have a really slick proof. Oh yeah, okay. So we just merge the top fractions actually. Yeah, so we'll merge the top fractions. We have this limit. In the top we have, so the top is 1 over y minus 1 over x. To merge these, we'll get y over xy, and over here we'll get x over xy, and we merge these, we get x minus y over that. Alternatively, we could just have xy just like that. Yeah, because this is just some simple algebra. And then this is just the limit as y goes to x of our fraction 1 over xy, so negative 1 over xy, which is negative x to the minus 2 by continuity of reciprocal. And also, yes. So we can actually add some text here. This follows from and some algebra. So there's the proof. Oh, that's not in the right place. Let's put that there where it goes. So that's the proof for a derivative of reciprocal. You could, in theory, generate the quotient rule this way. Although, now that I think of it, well, in the first place, I don't think I've used the quotient rule gosh, at all. I don't use it. Yeah, I'm also not sure if it works in general. Cancellation is really strange. It'll definitely work if the denominator is a unit, if it's always a unit, if you can always cancel. We might not necessarily know that though, so we can just add a note here. So we might just add a note to do the quotient rule. Maybe that'll work out. I'm actually not sure, because I've never done it. In the case where the denominator is not a unit, I mean, I have no idea what'll happen. I actually have no clue, which is interesting. But we'll leave this here as a note, and maybe we'll try that later. But that's not in either of my previous drafts, so I'll just leave it. So the next theorem we have to sort of import over into this new draft is, so there's two more, I think. We can maybe try to look around and maybe we can find something else, but the first one is if we have a function which is differentiable in a convex set, then actually the difference quotient is always defined. So that's actually really useful for, it just sort of makes everything simple. So we'll say let fg map s to a b differential, oh sorry, one function, f map s to a be differentiable and s be convex. Then for any x, y, and s, we have f of x minus f of y is proportional to x minus y. So this essentially means that if we have a convex set and we're differentiable in a convex set, then this difference quotient is always defined. So in our original statement, we said of our derivative, we said, well, we might not know if this is always defined, but in order to have the derivative defined, let's just say eventually, you know, for some y in a neighborhood of x, the fraction is defined. But this is saying, in fact, if our domain is convex, then the difference quotient is always defined. And so we can load this up with a proof. So this is going to be a little easier than the original version, and I roughly know how it goes. So we want to say, so first and foremost, we want to say, so we'll consider sort of a subdomain. Instead of S, we'll say let L be the set of tx plus 1 minus ty such that t is in 0, 1, which we notice is subset to S. Since f is actually, we can actually just take a simple case. So take the simple case where S is just this line segment. So if we take this case where S is this line segment, then we can say since f is differentiable, then we have we're going to say the derivative f of x is defined so as so there is a neighborhood, let's say U subset to L such that, over which y in this neighborhood U has the fraction f of y minus f of x over y minus x defined. That is, or sorry, rather, this is redundant. Instead of x and y here, let's do a and b to make this a little too many variables. So take the simple case where blah blah blah, x is a, y is b. So we have a line 7. F of a is defined. There's a neighborhood. This, let's say a in u, over which y in u has the fraction y minus a over y minus a defined. That is f of y minus f of a is proportional to y minus a. So we can write, instead actually, we can say there is a map, or sorry, a subset of u prime subset to this closed interval over which, oh gosh, yeah, let's define a function. Let's define a function for this line. So for convenience, let L of t be equal to ta plus 1 minus tb. Since f is differentiable, f of a is defined, so there's neighborhood, blah blah blah. Equivalent, we can say there's a subset, u prime subset to this, over which f of lt minus f of a is proportional to lt minus L0, because that's A is L0. So this neighborhood, so we have, okay, so, oh my gosh, okay, so I think what I want to do, so I know how this one goes. It's very complicated. I think we just want to use a subset, connected set argument. So S is this line segment. Let X be subset to S. Be actually be defined by X is the set of Y and S, yeah, such that this proportionality is true, but with A here and Y here, and A here and Y here, or rather AY, sure. Okay, so since f is differentiable, f of a is defined, so there is a neighborhood, yeah, so there is a neighborhood of f of a, yeah, a neighborhood f of, over which, oh yeah, okay, so notice that for each y in S, we have y minus a is is equal to, so, oh gosh, okay, yeah, we can do that too. T in 0, 1. We have TA plus 1 minus TB minus A as equaling, when we sort of solve this out, so we get T minus 1 here, and we can also factor out T minus 1 times A minus B. So if we have y as, actually we can say y in S with A not y and some z proportional to A minus y, then also z is proportional to A minus b. So we want to kind of try to use this fact. So we have a line segment and we want to say, if you can divide by one of the distances, one of the differences in this set, then actually you can divide by A minus b. That's sort of what we want to say. So so we can actually say for any xy in S of, or sorry, just in S with x y, we can find TS in 0, 1, so that x equals AT plus 1 minus T B, and y equals T SA plus 1 minus SB, and then x minus y is equal to, we'll get T minus S A plus S minus T B, which is just T minus S times A minus B. So generally, and actually we can say instead of x not equal to y, we can say this and this, so generally x minus y is proportional to A minus b. Conversely, if x is not equal to y, then also b minus a, or A minus b, is proportional to x minus y. Okay. So we can say now, let x be this set, so the set of y and s, such that f of a minus f of y is proportional to, where'd we go? Okay. That's it. Okay. I did it twice. That's funny. Okay, so so essentially each difference in this sort of space is proportional. We can also say, we could alternatively frame this whole thing. We could actually really just do that as, instead of t times a plus 1 minus t times b, we could actually reframe this as, we could say, well, this is just ta b minus tb. So actually this is just t times a minus b. And that's actually really simple. Yes. Okay, so we have this sort of characterization. So we have this whole thing, t is 0 to 1, it's a line segment, blah, blah, blah. So let X be the set where of Y and S, such that f of A minus f of Y is proportional to A minus Y. So we can also say that this is equivalently equal to the set. So we can say in the case, sorry, rather, for any Y, oh yeah, okay, let's do that instead. So proportional to A minus B, that's actually what we want to do. Let X be the set of Y in S such that this difference, f of A minus f of Y, is proportional to A minus B. And so we can say, since f is differentiable at A, then there's a neighborhood containing a subset to the line L, or subset to S, over which each y in U has the fraction oh yeah, we can also do that. So, okay. Since 0 equals A minus B times 0, then 0 is proportional to A minus B. And so 0 is an X. Next, we can show, we can actually show that this is going to be both open and closed. So take some, so suppose we have some y in X, or actually rather, some y sub n in X with limit point y sub n goes to some point y, then each, or rather then, since f is continuous, we have f of A minus f of y, y sub n goes to f of A minus f of y, and since all f of A minus f of y sub n are in this set A minus B times A, which is a closed set, then this is proportional to A minus B as well. So y is in X, and X is a closed set. So this proves that X is a closed set. Next we want to prove that it's an open set also. So we're saying take the simple case where S is a line segment. And so if this is true for all the line segments, then of course it'll be true in general. So take the case where S is a line segment. Let X be this set where f of a minus f of y is proportional to a minus b. 0 is in this set because a minus z is non-zero, and we can just write it as 0 equals a minus b times 0. So 0 is proportional to a minus b. Or sorry, not 0. 0 is this, 0 is proportional to that, and so actually I want to say a is in x. So x is non-empty. So x is non-empty because it has a in the set. Blah, blah, blah. Yeah, so x is non-empty. From this, we have, if we have a series in x tending to a point, so some limit point of this x, since f is continuous, and S is closed, then f of a minus f of y sub n limits to f of a minus f of y, and since all of these terms, f of a minus f of y sub n, these are all in this set, they're all proportional to a minus b. This is a closed set. This was one of our earlier propositions. Then this limit point is also proportional to a minus b. So y is an x, and x is a closed set. So we have shown that x is sequentially closed, so it's a closed set. It's non-empty. Now we just have to show that it's open. And that'll show that x is actually the whole set S. So now, in order to show that it's open, we can say take any y in x, then since f is differentiable, eventually the difference quotient there is a neighborhood, and we can rephrase these. So instead of doing y, we can just do x. Just change this variable name so it's a little more consistent. Okay, so take any x in x. Since f is differentiable at x, there is a neighborhood U subset to our set S, over which the fraction, and our fraction is f of y minus f of x over y minus x is defined. Find st in 0, 1 such that x is b plus t times a minus b, and y is s times a minus b plus b. Then y minus x is just s minus t times a minus b, so that this fraction f of y minus f of x over y minus x is simply the same as, in the bottom we'll have a minus b, and in the top, we can also have 1 over s minus t. this is proportional a minus b, and we get oh yeah, okay. We have this fraction minus this other fraction will have x minus a is just y. So finally, we get this is proportional to that, and y is in x, so that u is a subset of x, and x is open. And that's pretty much the proof. So let's just summarize these things. So we'll say take the simple case where S is this line segment. Then we can use the, and let X be this set. Then we can use the connectedness of S to prove that X is X equals S. Okay, so first we have this, so X is not empty. Then we have some sequence, blah blah blah, so X is a closed set. Now we can say take X and X, so that F is differentiable, there's a neighborhood over which all of these Y have this fraction defined. Then we can find S and T such that this is that and that's that, so this difference is this. So that this fraction is equal to that, so we just pull out this factor of S minus T, so f of y minus f of x proportional to that. Furthermore, this fraction, if we just subtract this other one, this will become this. So this is proportional a minus b, y is an x, so u is a subset of x, and x is open. And then we conclude x is non-empty, open, and closed, while S is connected, then X equals S. So this follows from the connectedness of S. So if we say take S to be a line segment, the only closed and open to sets, subsets of a connected set are the empty set and the whole set itself, using so here we're using the topology of S, the subspace topology. So X is open in S. Yes, so X is open in S, and it's closed in S. And it's non-empty, because it has 0 as a point. So X equals S. Now, what we can do is, actually we're done. X equals S. So in particular, B is an S, and we have f of B minus f of A is proportional to A minus B. We'll flip these around. Yeah, let me make sure I've got all these. It doesn't really matter too much, but I want to make sure I'm consistent on this. Yeah, so if we take furthermore right here, flip these around. Excuse me, I had to sneeze again. So we flip this around, and we get so a minus y. So a minus y is proportional to that, and y is an x. Okay, yeah. So use a subset of x, and x is open. Since x is non-empty, open, and closed, while s is connected, then x, we should say, non-empty, closed, and open relative to the connected s. Then x equals s, so in particular b is an s, and f of a minus f of b is proportional to a minus b. So this takes care of this special case where our set is a line segment. For the general case, where S is not a line segment, we can just let L be the set of t times a minus b plus b such that t is in 0, 1, which is a subset of S. And F is, and B, or rather, of F to L is still differentiable. So in the case that we don't have a line segment as our domain, we can just say let L be this subset, and the restriction of F to L is still differentiable, and still applies. The above proof still applies. And actually, let's we can shuffle these around. So we'll say so in the general case, we can let L be this set, and the restriction of F to L is still differentiable. So so let L be this line segment, L subset to S by convexity, and the restriction of F to L is still differentiable. If we can prove the claim while assuming S equals L, then it holds in general. this fraction defined? So we can find S and T. Okay, this all looks good. Nice. Okay. So this proof shows us that if we have our function differentiable in a convex set, the difference quotient is always defined between any 2 points in that convex set, any 2 non-equal points. So that's nice. So to recap this proof, what we essentially do is we're going to take, for any 2 points, or 2 points A and B, we're going to take the line segment between those 2 points. And then because of convexity, the line segment is a subset to the overall domain S. And if we restrict F to L, this is still differentiable. F will still be a differentiable function with respect to L, the domain L. So if we can prove the claim while assuming S equals L, then it'll hold in general. Because if we can prove f of A minus f of B is proportional to A minus B, we just prove it for the restriction. Yes. So in order to prove the claim for the line segment, we let X be the set of X in a lowercase x in L in that line segment, such that the difference f of A minus f of X is proportional to A minus B. So we're going to use the connectedness property to prove X equals L. So first we notice that 0 is in the set because of this zero product property. So A is in X, sort of trivially, so X is not empty. Next we suppose we have a sequence in X with a limit point somewhere in blah blah blah, with a limit point xn goes to X in L. Since F is continuous and L is closed, then this difference quotient f of A minus f of this xn also limits to f of A minus f of X by continuity of F. Since each one of these differences was, so by premise, each one of these differences was in our set L, each one of these points was in our set L, then these differences are proportional to A minus B times, which means they're in the set A minus B times A, times our, this set Blackboard A times A minus B. That's a closed set by one of our theorems. So it follows that this limit is also proportional to A minus B. So the limit point X is also in the space big X. So big X is a closed set. So that's non-empty and closed. So then to prove openness, we say, well, F is differentiable at any point lowercase x inside this space big X. So there's a neighborhood of X, which is subset to our domain L, over which X is not equal to Y. Over which any Y, which is not equal to X and in U, has this fraction being defined. So because it's differentiable at X, as Y approaches X, eventually this difference quotient has to be defined. Then we just find S and T, so X and Y both lie on this line segment L. So we can rewrite them as just, some B plus some coefficient times A minus B. When we take their difference, we just get this product, A minus B times S minus T. And this means that this original difference quotient with X minus Y in the denominator can be rewritten as a difference quotient with A minus B in the denominator. And because we get that, then f of Y minus f of X is proportional to A minus B. And then we can just subtract off, so we know X is X minus f of X minus f of A is proportional to yeah, f of x, oh gosh, f of a minus f of x is proportional to a minus b. So we can take that and subtract off the f of y minus f of x part, and that just turns out to f of a. When we combine the fractions, we get f of a minus f of y over a minus b, so that f of a minus f of y is proportional to a minus b. This means that y is in the set capital X, and since y was just an arbitrary point in U, different from lowercase x, then all of U is a subset of x, of the X space. So X is open. Since X is not empty, closed, and open relative to the connected set L, then X is all of L. So in particular, B is an X, and we get this proportionality. F of a minus f of b is proportional to a minus b. So this proves that we don't have to worry about is the difference quotient going to be defined. If we're in a convex set, then it just sort of always works. And we don't have to worry about whether or not it's defined or not. All of these other results don't necessarily restrict us to a convex set. Actually, the only restriction we've made is that the set has to have no limit, or sorry, no isolated points. So you can take a limit to any point. That was the only restriction we made. But we will use these convex sets more in the future, especially when we get to integration. Convex sets are kind of indispensable for integration, or at least locally convex sets are indispensable for integration. The last theorem that we have in our original draft is we're proving, in our original draft, we had proven that if a function was differentiable in a neighborhood in a particular way, then it's continuously differentiable. So we don't actually have the same type of derivative being defined. So this is one that I'm actually not sure how exactly we'll sort of port it over. So I do know that in some contexts, standard differentiability and this sort of stronger type of differentiability end up being equivalent. So actually this stronger type of differentiability is, I've called it perfect differentiability. It's where instead of having two variables that both limit, instead of having one variable that limits to sort of the point that it's going to, you have two variables that independently. So a difference quotient is essentially an average slope between 2 points. Usually when you take the limit, you take one of those points as being fixed and the other point having some delta added to it, and you limit them to that place. But you can define it in a different way where you have both of the variables moving at the same time and they're both sort of independently going to this point, with the only restriction being that they're not equivalent to each other, so the denominator is never 0. So that's how we had defined it originally. And it makes a lot of proofs a lot easier, actually. So some of the properties we use, so one of the properties we use is that if you have that sort of differentiability, then you actually get continuous differentiability, or that the derivative is continuous in a neighborhood of, for any point where it's differentiable in a neighborhood, you actually get continuous differentiability. That definitely won't work in the general case. So we have to have a domain, the domain has to be a neighborhood, which we might not always have. So I want to see if there's any way for us to maybe define that in a different way. And I think at this point, I probably will not be able to write. Well, I could get back to this later. So what I'll have to do is I'll probably have to look through this and see what we can do about to what extent this different notion of differentiability is required. For now, I think I'll go for just a little bit longer, and we'll use what we have now to prove some more stuff about power series. So we'll go back over to our modern draft, and we'll start writing some more theorems about power series, and we'll get back to to derivatives. I think we'll probably get back to derivatives later, not quite yet. We'll just sort of leave it where it is now, though. So in power series, what I want to prove is that power series are differentiable, and that's what we'll prove. So down here, okay, so we want to prove that they're differentiable. So we've already proven that they're continuous. They convert to a continuous function, which is sort of required. So let alpha be in a coefficient sequence for a power series, and x naught is also a starting point with, we'll assume the phi of alpha is less than infinity, so it has some convergence. And we'll say let u be, we wanted to have this pre-projection, this whole domain of convergence. So say let u be this set, and define f, which maps u to R space A as the power series. So we've got, okay, so we have coefficients A, center point x0, with phi of alpha being less than infinity. U is our open sort of pre-projected cylinder set, and define f, which maps u to A as the power series f of x equals summation across all n of x minus x0 power n times alpha sub n. Then f is differentiable to f prime of x is the summation n equals 0 to infinity, and we have n times x minus x0 power n minus 1, and actually we'll do the lower bound. Instead of n equals 0, we'll do n equals 1, and then we have our alpha sub n. So this is what we want to say. So in order to do this, I believe originally I just did some really awful approximations. Something else we can try to do is to say, possibly we could say a uniformly convergent series of differentiable functions is differentiable. That's another thing we could say. In order to do a proof like that, so I believe that's normally that is a theorem Okay, let's see. So the limit of the sequence of derivatives, uniform convergence of the sequence of derivatives, plus the convergence of the sequence of functions at least one point. So in order to ensure a connection between the limit of a sequence of differentiable functions and the limit of the sequence of derivatives, the uniform convergence of the sequence of derivatives, so uniform convergence of the series of derivatives plus the convergence of the sequence of functions. So this sentence here is saying if f sub n is a sequence of differentiable functions on the unit interval, and the limit and their limit exists for some point, so that's fine, and the sequence of their derivatives converges uniformly, then f sub n converges to a function and f prime is the limit. So there's a lot here we can't use. Actually, because we have this closed interval, our topology is not compactly generated. So this actually won't necessarily work for us. But we can try maybe something else. Let me see, there's probably a proof. And we can try to tear apart this proof to see if we can get any insight. The stack exchange always follows through. Okay, so so here what this person is doing, they're saying fixed units interval existence is equal to this, that this is f prime of c. I accidentally bit some of my nail polish off. Okay. Oh, I know what we can do. As we take a limit to a point in our space, despite the fact that it's not locally compact, we can still put the entire sequence inside of a compact set. So if we have a sequence approaching a point, then we can place that entire sequence inside of a compact set. And in particular, if we have some neighborhood of that eventual point, eventually our sequence will be in that neighborhood. So we can actually assume we've taken some compact set which is subset to that neighborhood, even though it's not compactly generated. So we don't have, or sorry, not locally compact. None of our neighborhoods are compact, actually. None of our open sets. Okay, let's try that. So down, not here, up here, I think we can prove, so we have all of this. So what we're going to do is, we can say, oh gosh, let me think. Okay, so I think we can say, okay, so, yeah, okay, so, let S be subset of A, be locally convex, or rather a locally convex subspace, and we can say let f sub n be sequence of functions indexed by mapping, indexed by naturals mapping S to our space A, B actually let's do this, we'll just do it easy, be convex. Fn is a series of functions which are differentiable. What's impressive feat? So these are differentiable, and we'll have and so these are all differentiable, and the series f sub n prime limits and okay, so yeah, goes to, there is G mapping S to A, having Fn prime go to G, with converge compactly, then oh sorry, that's not what I want. Oh yeah, that is what I want. Okay, so let Fn be a series of functions with f sub n going to G, Fn goes to G, and okay, differentiable functions. Fn go to F, and Fn prime go to G prime, or some converge compactly for some G which maps S to A. Okay, so let Fn Fg map S to A be a series of differentiable, sorry, be a series, be functions with Fn goes to F and Fn prime goes to G prime, converging compactly. Then F prime equals G. That's what I want to say. Something to this effect we're going to prove. I don't actually know if it's going to be this exactly. We'll find out. I haven't done this theorem yet, but I think I have an idea of how this is going to prove, I have an idea of how this is going to be proven, how we can prove this. So all we have to do is sort of find a sequence. So okay, so let y sub n be series sequence indexed by naturals. Oops. In the domain S, have y sub n go to, and actually instead of, yeah, go to X in, okay, yeah, so let X be an S, and y sub n be series, a sequence with y sub n goes to X. So S is a convex subspace. Okay, so we're going to take some sequence y sub n converging to x, then we're going to try to find a compact set. But eventually what we're going to set up to is we want to say these derivatives f sub n y sub m minus f sub n, so x, y sub m minus x, this will go to f sub n prime at x, and this goes to g compactly. Okay, so subset S without the point x. So we have these sequence of points, they're tending to x, they're never equaling x. And we want to show, so we want to find, okay, so find a neighborhood. Oh, it's already convex. How are we going to do this? So, I think what we want to do is show that this fn, these fractions of fn, so these converge to fn prime, which converge in to g of x. I think what we want to do is we want to put a close bound on this difference between these two expressions. We might need to assume that f prime is differentiable. Yeah, so we want to, so we know that this this whole term here is tending to, with m, is tending to fn prime, and this converges compactly to g. So what we want to do is we want to take this difference here, we want to show that this is particularly small in some sense. So we want to show that as we take m and then n to infinity, that this will go to 0. So the way to do that is we can show, we want to find a bound across all let me think. Okay, so because this converges compactly, so because this converges compactly, then if we take a of f sub n prime of x, and we subtract that from, oh gosh, Okay, yeah, so let's just merge these first. So this will give us fn ym, and we're subtracting sort of minus fy sub m. And then this one will give us minus fx. And we know that if we can, so this converges compactly, which means for each compact, yes, so as across all n, or across all m, we can form a compact bound which tends to 0 with n. And then I think we can say, so essentially we just want to make some small, okay, so x is s, and sequence y is subset to s without this, and this goes to that. Okay, so we can say well, how do we find a compact set? I want to say if we take a compact set in A and then intersect it with a subset that's also compact. I think that maybe that's actually not true. Maybe if it's, no, that's not right. Oh, I know. Maybe we can use sequential compactness by essentially just sticking together a bunch of line segments from the different y sub n points. That actually might work. Let's see. Well, let's just leave that for now. So find some compact set. Let me just look it up. Oh, actually, of course. Let K be the set of X union the set of Y sub n which is a subset to S. K is K is sequentially compact and thus compact. Okay, so K is sequentially compact and thus compact. So, so we have a compact set. This means that over K we have f sub n prime going to g prime, not, yeah, g, let me fix that. Going to g uniformly. So we have the limit, we have some bounds b sub n for which supremum of, we have our sets of differences f sub n prime of x minus g of x, such that x is in K. Actually, we can do y instead of x, because that makes more sense. Supremum of the absolute difference of fn prime of y minus gy as being b sub n. Actually, we can just say, so we have b sub n, let b sub n be this, so that b sub n goes to 0. Now that we have this, so this bounds this, not this one. Let's see, what does this proof do? Okay, I see. So they're just saying distance between, so we have this original term minus this thing plus this exact thing minus that thing plus this thing minus g of c. Okay, so let's just see what happens if we just do that, but with our a function. So that's, yeah, so the difference quotient for f we'll do absolute value. We have f of y sub n minus f of x over y sub n minus x. And we're subtracting g of x. This will be bounded by, we have from here we have f sub n y sub n minus f of x. They have, yeah, so I have the first term, the second term is x plus the third term, which is this second term here, minus f prime, f sub n prime of x, plus absolute value f sub n prime of x minus g of x. Okay, that's really long. So we can put this in an inline environment. We can take this whole thing for now, shove that right in there, and when we do this, we can actually sort of have that plus, oops, have that, and then plus this thing. Let's see how that looks. Okay, yes, so we have this divided by that, plus that, plus that. So we know fn prime of x minus g of x. This is going to 0 as n goes to infinity. We know that fn, this whole thing, this goes to 0. And then all we need to show is that this goes to 0. So this would be, okay, so, yeah, so we have this, blah, blah, blah. And I think, okay, I think they were gonna show that's not gonna help me. Okay, so what's going to happen next? So we can merge these if we want. Oh, also I did a goof. Let me fix that. We want to do y sub m here. I fixed that before. Okay, that's better. So we don't know we do know this goes to 0. We do know this goes to 0, and then it's just a matter of this. This will go to 0 with what terms, actually? We want to do a limit in terms of y as y goes to infinity. We want to show this goes to 0. So this fraction will at least always be defined, because we do know that f of x is differentiable. I wonder if this becomes easier if we assume f is differentiable. I think it does become easier if we assume f is differentiable. So if we have this whole term, this is just this whole first term. We can merge these as the first one will be actually let's put these together so we can shorten this up a little. Yeah, so this term well, okay, so if we take m to infinity here, this will end up being 0 for each n. And here we just have some freedom. If we merge these, so we would get fn y sub m, so this will be negative, and we have this negative fx, is that correct? Did I do that right? This should be f sub n, I think, is actually what it is. Yeah, that's right. Yeah, okay. And we can also put this around to the front. And rearranging these, so this will make it look a little better. G minus that, G minus this, and then this thing minus that thing, and this one minus the last one. And this last term is right, so let's take this whole thing, try that one more time. So when we rearrange these, so I'll turn this into a plus, and we'll flop these two around. Then we'll take this minus f sub n of x. Yeah, okay, that's fine. That'll go over there, so we have two x's. This will go over there, so we have two y sub m's over there. We can also flip these the other way, like this. As n goes to infinity, this will go to 0. And we're just taking this m limit, so we can do n however we want. And likewise for this one, this will go to 0. And I think that's all that's necessary. I'm actually not sure why this should be any more complicated. I also think we probably don't need to assume that f is differentiable. We made that assumption so that this would be a little easier. I think we don't need to make that assumption though. So if we have, so essentially we have this g of x minus these f. So we want to show that f prime goes to g of x, or rather that the limit as m goes to infinity of this fraction goes to g of x. So that if we subtract g of x, this will go to 0. Well, if we do this by the triangle inequality, so we get our g of x, we get, and from sort of the triangle, we have g of x minus this fn prime at x. Then here we have fn prime at x minus this other fraction. And then we have that same fraction minus this final term, which is the same as this one. So we've just sort of, instead of just going from g to this other one, we've sort of taken this long way around where we've gone from g to f prime to this other fraction to the final term. We know that, so all we have to do is take a limit as m goes to infinity. If we take this term here and limit n to infinity, so this is less than or equal to this for all n. So if we limit n to infinity first, this term will go to 0 because fn prime limits to g, right? Fn prime g of x minus fn prime of x. Goes to 0. This term is f prime n, and then this term. So as n goes to infinity, I want to say this will go to 0. That's actually not true. So I'll have to keep that in mind. Actually, this one won't go to 0 with n. It will go to 0 with m, and it also we also have this term over here. So I think something that we want to show is we can show that as we take a limit over m, we don't want to show that this necessarily goes to 0 directly. We just want to show that it's bounded by something. So we can make you know, n large enough so that these bounds are below some critical value. And we do know that for each fixed n, this will tend to 0 with m. And over here, this will tend to 0 with n. This will also be, oh right, because this, when we rearrange the terms of this fraction, we get this one. If we limit m first, actually, this one won't converge, I think. Hold on. Yeah, as we limit m first, these individual terms won't limit. So if we do n first, they will limit to 0. So this numerator will go to 0, and this numerator will go to 0 if we limit by n. But if we limit by m first, this won't even converge if we write them this way. Which is interesting. So this sort of standard proof they're doing, they're showing that these difference quotients in terms of for each c is converging uniformly, which is interesting. Well, that's just not useful. We can't use that here. We don't have the intermediate value theorem. Or the mid-value theorem, rather. But they are showing that these corresponding, these ones, that these converge to this uniformly with n, I think. Yeah, only with n, which is true, I think. Maybe. We'll see. We'll see. Maybe if we can prove these converge uniformly with n. So instead of doing this other thing. Yeah, okay. In any case, this will go to 0 regardless of how we do it. This will go to 0 with n. No, this will go to 0 with m. And it'll also go to 0. No, it won't go to 0 with n, but it will go to 0 with m. This will go with n or m, and n. This with m. So eventually, regardless if we take this one will go to 0 with m, regardless of how we take n. So long as we take m. So this will go with m, this will go with n, and it's just this one. So we need to show that this one goes when we take m. That there's some bounds we can take on this one that'll go to 0 with m. To do that, we can show there's perhaps sufficiently large n to make formally okay, I know why. Okay, if we can show, so because we have pointwise convergence, if we can show uniform convergence with n across this k set, this compact k set for these y sub m's, if we can do that, then what we can do is and that should probably be true, I think. So if we can prove compact convergence of this to this with n, then we can find sufficiently large n to make this difference bounded across all the y sub m's. That's what we want. That's what the other proof is trying to do. Do we actually have that though? So they've used intermediate value theorem. We don't have that. instead what they've done is, by applying the mean value theorem to this, we can find, for each of these sort of average slope terms, find some alpha. I think they shouldn't be the same alpha. I'm actually not sure if that's the case. Okay, all they're doing is they're finding some value of alpha such that this difference is just these f primes for m and n. Okay, I see. And these m and n's are suitably close to, because they're converging uniformly to G, so their difference will also converge uniformly. So you can pick large enough n. Okay. So actually what you want to do, instead of showing that these this sequence converges to this, actually what you want is show that for a different n and m, that the differences of different terms are comparable just to the differences of these derivatives. Another thing that we could do, instead of using mean value theorem, which is useless to us, we can say we actually just want to show that these different quotients converge to oh gosh. I don't know if this proof is going to work out in this way. Let me just try. So we get our compact set, and we want to show that these sort of converge really nicely. So Fn prime goes to G uniformly, so we can let Bn be the supremums of these differences. And now actually what we want to show, so because Fn prime of y is going to 0, yeah, okay, that's it. Okay, so because Bn is the supremums across all y, and Bn goes to 0, because Bn is going to 0, we can also put Bn in a compact set, and that actually gives us uniform, sort of a mutual uniform convergence, I think. Okay, so let's try to work something out like that. So we have, let's do Fn ym minus Fn x over over y sub m minus x, and we want to compare this to our Fm. I'm going to need another letter, y sub I. Why not? Let's just keep using more indices. Okay, so y sub I, Fm y sub I minus Fm x over y sub I minus x. So I want to see if we can sort of put these close together. So we know both of these terms, this goes to, with I, it'll go to f sub n prime of x minus f sub n m prime of x. And as n and m are very large, this will then tend to 0 uniformly. Okay, maybe what we can do, so we know we want to take a limit of m, and n here doesn't matter. So actually what we want to do is we want to select an n, which is as good as possible, so that this whole thing goes to 0 when we just, so n as a function of m. We know that so long as n goes to infinity, this term will sort of vanish. And actually, yeah, so this term will vanish. So as long as n goes to infinity, this will vanish. Over here, likewise, if we have, if we have m go to infinity, this will go to 0 first, if we have m go to infinity. If we have just n go to infinity, this won't go to 0 yet, but if we go have n go to infinity while m stays small, then this will just be the difference quotient for just f. If we assume f is differentiable, then this will go to 0 with n still. All we need to show is that this sort of term will, because right here actually, for this third term, we know that as we take, if for each fixed m, as we take n to infinity, this term will actually zero out. And the reason that it'll zero out is because this f sub n of y sub m will limit to f of y sub m. Those will cancel. And likewise, this f sub n of x will limit to f of x, and those will cancel. So this will limit to 0 for each fixed m. So we can find some lower bound on n, for which n has to be. That'll make this, for any fixed m, we can make this as small as we want. So we can pick n to be as small as we want. Or, instead of making it as small as we want, we can just find a lower bound after which it'll stay small, regardless of how else we'll pick m. All we need to do then is to pick n large enough so that it's above this bound, and also so that this term, this whole expression, goes to 0. And we can also do that because as n goes to infinity, this whole expression tends to just the difference between f prime and this fraction. So if we assume f is differentiable, then this will be easy. So it'll just limit to f prime minus its own fraction. And we know that that expression limits to 0 with m. So all we have to do is pick n sufficiently large also that this expression is rather close in some sense to its own that this expression is rather close to what its difference quotient should actually be. So how would we do that in a precise sense? I think probably what we can do is we can do that on each projection. Actually is what we can do. Okay, so we'll do that. So I'll scrap some of this. So I think I've got it with this. So let x be a point in our space S. Y sub n is going is a sequence in that space S without x. It's limiting to x. We're gonna let actually we don't need this. So if we assume f is already differentiable, then we get this for free. So suppose, or rather, for each n and m in natural numbers, also I'll change the index for y to have m's so that that's a little consistent. So for each pairs of these, actually we'll do n, m, and k. So we'll consider the following decomposition. So we have this is bounded by that and then by that. So actually we have nm natural constraint decomposition. Okay, and then so that as n goes to infinity, we have okay, so the first term, f sub n prime of x goes to g of x, implying a of g of x minus f sub n prime of x goes to 0, And we also have f sub n y minus y sub m minus f sub n of x over this fraction y sub m times x goes to the same fraction, but we don't have any m's. And that implies that this term goes to 0. Okay. That's a value p sub k actually we'll leave that for a sec still. Term plus this term, flip these around. Hopefully this will fit. Okay. This is more about how you do math. Which part exactly is that? Looking at math stack exchange and figuring out how to make any sense of it. Yeah, I mean, it's part of the process, you know. Okay, so this goes to 0, this goes to that, implies this goes to 0, and we also have this term, yeah. This one goes to 0. This thing goes to the 0, and this thing goes to let's put a different alignment. I'll align that. That's not going to work at all, actually, if I do that. Let's just get rid of this symbol. Okay, so that goes to 0, that goes to 0, and this goes to that. With n. Okay, so fixed sum, k, natural number, index. And for each m, find m, n is a function of m, such that So we have this whole thing. So actually I can erase that. Let's also turn this into a gather. Okay, so we want to have this projection less than 1 over m. So instead of n, we'll have n's of m. Oops, okay. So this projection will be less than 1 over m, and this projection will be less than 1 over m, and in each of these we have n now as a function. So we'll replace that in here. That'll be there, and there. That's fine. And then over here, we have there, and there, and there. So we'll do yeah, we should do, because this thing is going to that, we should actually just reframe that in terms of this. Yeah, we definitely should do that. Okay. We can also, we don't need this assumption anymore, it seems. I have no idea what my assumptions are doing. We'll figure that out. Yeah, so actually what we want is, because we're going to end up with this term here, it'll get really messy if I make it any bigger. Actually, maybe that's fine. So we have this plus fn prime x minus f prime of x plus we have okay. F prime of x minus, we have a fraction, fy sub m minus f of x over y sub m minus x, and then we have yet another fraction. We need to end up with f with them. Oh, that's what we need to end up with, huh? But aren't we already done? No. Is this trivial and am I dumb? I think if we assume f is differentiable, this becomes trivial. Hold on. G of x, these f things. So g to f prime n to f prime, and then f prime to this fraction there. With n, this converges pointwise, this converges pointwise, and this just converges with m. Yeah, this is trivial. If we assume that that f is already differentiable, which we don't need to do here, this becomes trivial, because we do just have g minus this fraction is bounded, so we go from g to f prime sub n to f prime sub to f prime, and then to this fraction. G minus f prime n, so f prime n goes to g. Oh, okay, that's why it doesn't work. Okay, let me do that better. So from f prime, we actually need to go not to, sorry, from f sub n prime, we don't need to go to f prime, we need to go to fn, yeah, this fraction. This is so gross. So we need to go f sub n prime, and then we get f sub n prime x minus this fraction, right? And that means we don't need to do this, it's not there. Fn prime, and then we get fn prime to its difference quotient, and then we go from fn's difference quotient to f's difference quotient. And then we go from f's difference quotient. Then we go to f prime. And the reason that we can do this is because we're assuming, we're assuming that f is differentiable. So we're actually not proving very much for now. Let's cap this out at, I guess we'll just do one term per line. We'll see what that looks like. That seems okay. That's kind of easy to follow. I could also align it with, instead of aligning it with this plus sign, I could align it with this difference. That I'm not sure which one of these would make it more clear. I really don't like that. Also, I'm missing a whole bunch of parentheses. Let's see, where did I mess that up? Yeah, why am I missing parentheses? What the heck? It's on every single one of these. Oh, I see. It's the second line, I think. I have no idea. Weird. Maybe it's because I have this on the inside. Yeah, I guess that's why. Okay, I guess I can do that. That's fine. Yeah, so I guess if we just assume that we've got... Let me also move that. There. Yeah, so if we assume that we have a derivative, we just go from g to f prime to f, the difference quotient of fn, so g to fn prime, which we know converges, fn prime to the difference quotient for fn, and then from the difference quotient of fn to the difference quotient for f, and then finally the difference quotient for f to f prime. And the way that we can prove this is, so this goes to 0 with n, and this doesn't go to 0 with n. That's okay. Let's leave that for a sec. This goes to 0 with n, and this goes to 0 with m. So as we limit m to infinity, this will vanish. We can make, if we make n as small as we need to, this will vanish, and this will vanish. So as long as n and m are going to infinity in any, if n is going to infinity fast enough, this will go away and this will go away. And then all we have to do is here. Okay, so all we have to do is pick some, okay. Hold on. Okay, yeah. So as n goes to infinity, we have, for each fixed m, Oh, I did it again. We want to show maybe we just have to do this the long and ugly way. Yeah, also we don't need this last term. Yeah, okay. I guess we just have to do this the long way. Yeah, so as n goes to infinity, we have this goes to 0, and this term goes to 0, and this thing goes to that other thing. Okay, so fix some index k, and for each m, find n in terms of m. So I'll do a subscript instead of parentheses notation. This projection less than that, this projection less than that, and this we want okay. Well, I think maybe I should think about this for a little while. I'm going to call it a day here. Thanks for joining me on this adventure. Yeah. Good night if you're on the East Coast, question mark. And I will be back tomorrow. What always helps? Yeah, you know, just a casual 7 hours of math. Yeah. But yeah, we'll be back tomorrow. I'll think about this. I'll think about this one, and we'll see what we can do. I know that with strong enough conditions, this should be true. But yeah. Yep. Yeah. Okay. Well, thanks for stopping by and watching. And I will see you later. Good night. Bye.